So we're going to start with section 10.5, which is devoted to what are called comparison tests. So now there are two comparison tests. One is called the direct comparison test. Usually we don't use the word direct. So whenever the phrase comparison test is mentioned, it means direct comparison test. Now this one is tricky, very tricky to use, and therefore used infrequently. On the other hand, the second one is called the limit comparison test, and this one is very useful. So we are going to devote more time, and we have to be very good at using limit comparison test. So let's study both of them. The direct comparison test says the following. So it says if there are two series, summation AK and summation BK. So there are two series with positive terms. That's always the case, so that's not a problem. So it says if AK is less than equal to BK, that means each term in these series are such that the A's are less than the B's. And if BK converges, the series BK converges, then the series AK also converges. On the other hand, if the terms BK are less than the terms AK, now this is term wise, like as if you're looking at it as a sequence. And so together with that, if the series BK diverges, then the series AK diverges. Now this sounds very confusing to begin with, but you have to be very careful, and here is the intuition behind it. So you can either understand this intuitively, or you have a table of integral tests which are posted on Blackboard, and you're most welcome to print it and keep it handy with you. You can obviously use it during your quiz and during your test, and so that you don't have to memorize any of these tests. But all the same, it's very important and useful to understand what's the logic behind this. So here we go. So here, suppose you have a series AK, which means A1 plus A2 plus A3, like that. So these are the elements of this series. Then you have another series BK, B1 plus B2 plus B3, and so on. So let's look at the very first one. What's the first one saying? So it says AK is always less than BK. So if you look at it graphically, what it says is AK is always below BK. So if this is B, suppose this is B1, then A1 is here. So this is A1 and this is B1, because B is always sitting on top of A. So if A2 is here, then B2 would be somewhere up. So A3 suppose is here, then B3 would be up here. The point is that B is always above A. Okay. Then it says the series BK converges. So this is the first thing that must happen, and the second thing is that the series BK converges. Now what does that mean? That means all these heights, remember series BK means B1, that means this height plus this height plus this height. So all these heights, when you add up, this adds up to a number. So let's suppose it adds up to 10. Then the series series AK, which is what? This A1 plus A2 plus A3. Now remember, these guys are always less than B's. So then this sum of A's would obviously converge. In fact, it will converge and be less than 10 because it's always less. So that's why it makes intuitive sense. On the other hand, if bk's are less than ak's, so if ak's are here and b's are sitting below, so a's are here and b's are sitting below, so I'm looking at the second case, and the series B diverges. What does that mean? That means these heights, all these heights, B1 plus B2 plus B3 and so on, diverges. So that means this sums up to infinity. So if the lower guys add up to infinity, then obviously the sum of A's, which are more than B's, will add up to more than infinity. So then the sum of AK is obviously infinity. So that means the series AK diverges. So that's the meaning of this particular test. Okay, so how do we begin with this? So you are actually given a series AK. So your given series is AK. Then you have to guess or come up with another series BK that does the above given job. That means somehow you have to come up with a series BK which either satisfies this or satisfies this. Then you can conclude something about your given series AK. Now this is tricky. I mean, it requires you to be inventive and it's usually tricky to use. So let's look at the first simple example. I want to study ln k over k. Now obviously the first thing is, what is my AK? AK is ln k over k, because my given series is summation of AK. Now, so this is the first thing. Second thing is the most important thing. Now I have to find something above or something below it. So that is the BKs that I'm looking for. Now if I find something on the upper side, then so suppose I come up with some BK here, then it only helps if the series BK converges. So only then it helps. Only then it's helpful. On the other hand, if I come up something on this side, some BK on this side, then it must be such that the series BK, so if I add up these BKs, then this guy should diverge. Only then it's helpful, otherwise it's useless. So that is the first tricky part. The second thing is, how do we find things in fractions when they are in fraction form, greater or smaller? So think about going greater. So if you want to find something on the greater side, then the numerator should increase or the denominator should decrease. That's how a fraction increases. So let me repeat. If you want to find something larger than this fraction, then you would increase the numerator and decrease the denominator. If you want to find something smaller, then you would decrease the numerator, or you would increase the denominator, because if you increase the denominator, you're dividing by a larger amount and your fraction would become smaller. So this is something to keep in mind. So let's see. So I have ln k over k. So suppose I want to go on the higher side. So I want to find something up here. So what can be larger than ln k, log of k? Well, k is larger. And if I keep my new denominator same, so I get k over k. Or I could even go k squared, because k squared is definitely larger than log k. And I can keep my new denominator same. So either one of them. So suppose, so this is 1 and this is k. But what must I have with this series? Suppose I picked this to be my bk. So suppose this is my bk. So that means my series bk is summation of k. Now summation of k is obviously divergent, because what is summation of k? It's 1 plus 2 plus 3 plus, so that is obviously infinity. But remember, for something on the right side, on the larger side, this must converge for us to be able to use the first theorem, first part of this theorem. So if I go on this side and I find these, either one of them, either 1 or k, it doesn't help because this series diverges. So this is useless going on this side. So how about if I go on the other side? So suppose I go on this side. Okay, so how do I go on this side? So what could be smaller than ln k? So what can be smaller? Well, 1 is smaller than log k, or 2 or 3, doesn't matter. Any number would be smaller than log k. And let me keep this as k. I don't have to change this. So 1 over k is definitely less than equal to log k over k. Now what can I say about, if this is my bk, what can I say about it? Well, this series bk is what? It's the series 1 over k. But I know this diverges. This is the p series, so I know this is the harmonic series. I know it diverges. So now what has happened is I have found bk which is less than ak, and the series bk diverges. Therefore I can claim that the series ak diverges. So therefore, since series bk diverges, by part 2 of that theorem, series ak diverges. Okay, continuing with the next example for direct comparison test. So here we have summation AK is summation K over K squared plus 1. So that means our AK is K over K squared plus 1. So now we have to try and find useful upper bound or lower bound. So let's try the right hand side first. Remember, we have to find something on this side. If we do find something on this side, then that series must converge for it to be useful. Okay, so what can we find which is bigger? So, and how do you make a fraction bigger? Either we increase this or decrease this. So this has to increase and this has to decrease. So in this case it's pretty easy. Suppose I keep my numerator k, but k squared plus 1 can easily be decreased to become k squared. So what is this? This is 1 over k. So suppose I choose this as my bk. So now the question is, what is this series bk? Well, the series bk is series summing up 1 over k, but this guy we know diverges. Therefore, it's useless. So again, going on this side, on the higher side, is not helping out. So let's try our luck on the other side. So if I want to reduce this, then I have to decrease this numerator or increase the denominator. So now this gets a little tricky. So suppose I keep my k as just k. Now I want to increase my denominator. So I have k squared, but now instead of adding 1, I'm going to put k squared there. So k plus k squared is definitely k squared plus k squared is definitely larger than k squared plus 1. So that means I was able to decrease this. Now what is k over k squared plus k squared? This is k over 2k squared, but that is 1 over 2k. So this time suppose this is my bk. Now what can I say about this series? So what can we say about sum of 1 over 2k? Well, this one we know diverges because this is one series. So this guy diverges. Now this is useful because the series on the left side, on the lower side, should diverge for us to come to any conclusion. So now we can say that we have found bk which is less than equal to ak. Second, my series bk that I found diverges. So these two together tell me that my given series AK diverges. So my answer is that this series diverges. Now notice how inventive one has to be able to find these kind of series to be able to use this test. Let's do another example. Okay, so this is my series AK. So that means my AK is 1 over K 2 raised to the power K. So I want to find bounds on either side so that something useful can be concluded. So remember, if I go this side must be divergent. If I go on this side, it must be convergent. Okay, so let's try finding something which is larger. So again, how do you make something large? You either increase this or decrease this. So how about if I keep 1 as 1, and in the denominator, instead of K, I use 1, and I keep 2 raised to the power K. So definitely this is less than this. So therefore this fraction is greater than this fraction. So what is this? This is 1 over 2k. But 1 over 2 to the k is same as saying 1 over 2 whole thing raised to the power k. So suppose this is my bk. So the next question is this series bk? That means if I add up 1/2 raised to the power k, what can I say about this? But this is a geometric series with r equals half. So that's great because this converges. So what have we found? First, we have found a bk which is larger. Second, we have found that the series bk is convergent. Series bk converges. So these two together implies that my given series AK converges. So this is pretty neat, but again, as I've pointed out, that one has to be quite inventive to be able to use these. And later on you will see that all these three series that I have considered could be done by some other test much more easily. So the conclusion is that this is not frequently used and is not important at this time. So don't fret over it. It needs a lot of experience to be able to use this test.